So it's bittersweet to be ending the Obstruction Bundle Zooming for fall 2020, but it's a pleasure to have Morgan Weiler from Rice University giving the final talk, and she'll be speaking on a sketch of why d squared is 0 in embedded contact homology.
Thanks, Joe. Yeah, and thanks for having me speak. So this is kind of a departure from some of the previous talks. I won't be talking about obstruction bundles at all, but I'm just gonna try and give you a roadmap to section 7 of this gluing 1 paper, and sort of how you can read it. Oh, can you not see my drawing? Doesn't seem to be working. That's weird. I'm going to try and screen share again. Okay, good. Yeah. I was very much relying on being able to draw my cartoons of holomorphic curves and not have to make the pictures on the computer. So yeah, so I'm giving you a sketch of this section 7 of this paper, mostly section 7. There's some pretty key propositions and lemmas that I just won't explain how to prove at all. Some of them are proved in later parts of section 7 of this paper, and then some of them rely on this paper by Hutchings called an index inequality for embedded pseudoholomorphic curves in symplectization. So that's relied on pretty heavily, and I've kind of hidden that in this talk. But if you want to know how to prove basically the key propositions that we use to do anything in ECH, that's the paper you need to read. And then you need to adapt everything from a mapping torus to a contact manifold. So, but in this paper, they explain how to do that when you have to do it. Okay, so just to give you a quick recap of ECH, you pick, so this is just the definition of the compatible almost complex structure you'd want to pick on a symplectization. So it sends the R direction, this R direction to this R direction. It rotates the contact planes positively with respect to d lambda and its R invariant. And what the setting that we're going to be in is a contact manifold with a homology class, a 1 homology class, and a generic lambda compatible almost complex structure on its symplectization. And the ECH chain complex is generated by finite sets of Rabe orbits of a contact form lambda on a contact manifold Y lambda. And an orbit set is a finite set of pairs where the first entry in the pair is an embedded Rabe orbit, the second entry is a positive integer, and we say that the orbit set is admissible if the multiplicity is 1 whenever alpha I is hyperbolic. So the generators are admissible orbit sets, and the total homology class of an orbit set is just the sum of the homology classes of the component orbits alpha I with the weights given by the mi, and so we consider orbit sets that are in a fixed total homology class. And we need to do that because we're going to define the differential using surfaces that interpolate between orbits. So we consider the set of relative homology classes of 2 chains with boundary, basically with boundary on alpha minus beta. And so these are the homology classes our orbits, our interpolating J holomorphic curves could possibly live in, or at least that their projection to Y could live in. And I guess, okay, so I didn't tell you where these J holomorphic curves live. These are J holomorphic curves in the symplectization R cross Y, where J is a lambda compatible almost complex structure. And so there's lots of different types of moduli spaces, but hopefully, if I add a Z to the end of a moduli space, that makes sense to you. So M superscript J alpha beta is the moduli space of J holomorphic curves with positive ends at covers of the alpha I of total multiplicity mi, negative ends at the covers of beta J of total multiplicity nj. So here alpha is equal to pairs alpha I mi, and beta is equal to all the pairs beta j nj. And if I add a Z, that just means I'm only considering those in the relative homology class Z. And then if I add a subscript 1, that means I'm not allowed to contain any covers of cylinders over elliptic orbits. So this is, I was actually surprised by this because I had not read this part of this paper. And so I had only seen the setup of ECH that doesn't use these moduli spaces without covers of elliptic orbits. But I'll explain to you how these spaces are involved in the setup of the differential. But first, we need to talk about the ECH index. So I don't necessarily expect you to understand what's going on here, but in any case, for a pair of orbit sets and a relative homology class, I can cook up this integer using this formula. This first part involves, this is the relative first term class. And this is the relative self intersection number. So basically, for the first term, you fix a trivialization of the contact structure along the components of alpha and beta, and then you compute the first term class of the contact structure over a representative of the homology class Z, forcing that representative to be constant with respect to the trivialization on the ends. And for the Q term, you compute the self-intersection of this representative, again, forcing the representatives to be constant along the ends. And then you add this sum of Conley-Zander indices. And then we can also talk about if I have a curve in the moduli space with ends at alpha and beta in the class Z, that I can just talk about the index of that curve, and that index is defined as the index at alpha, beta, Z. The important fact is that the ECH index adds. So if I have 3 generators, or not necessarily just generators, if I just have 3 orbit sets in the same homology class, and I have some other relative homology class between beta and gamma, then so here's my alpha, here's my beta, and here's my gamma. I don't know, maybe that's like a double cover or something. And I have some, curves or something. Then the index of the top plus the index of the bottom is equal to the index of the curve that goes from the top to the bottom if I add the two curves, if I sort of take their union. Or in the sense of the homology classes instead of in the sense of the curves if I add the 2 homology classes. Okay. So this is helpful when I'm thinking about the index of components of a building. So how do I define the ECH differential? So the first thing is a bit of notation. If I have 2 orbit sets, I can take their product, which is just take the union of the elements or of the Rabe orbits and then add the multiplicities. And then I can then divide an orbit set by another, and I can also consider the quotient of one orbit set by another. So if I have 2 cohomologous orbit sets, alpha and beta, that are admissible, so they're generators of the ECH chain complex, then the differential coefficient of alpha in front of beta is the sum over 2 homology classes such that the index of alpha, beta, Z is 1. And then the sum over elliptic orbit sets, which divide alpha and beta, of a count of the elements of this moduli space, which is curves from alpha with positive ends on alpha and negative ends on beta in the class Z minus R cross gamma. And then I'm not allowing any covers R cross gamma of elliptic orbits. So elliptic orbit set just means that all Rabe orbits are elliptic. So this kind of helps you. So these moduli spaces, I should have said this earlier actually, these are sort of the ECH version of moduli spaces. So they, this is the space of curves with total multiplicity on the Rabe orbit elements of alpha, of total multiplicity, the multiplicities that appear in alpha, and then similarly for beta. So I'm not requiring like a specific end, like specific Rabe orbits as the ends alpha and beta. So something, so if like some orbit appears in alpha with multiplicity 2, I can see curves in here that have 2 separate ends on alpha on that orbit at the positive end, but I can also see curves that have 1 double cover. Okay, and this this works out to sort of the regular way that we think about the ECH differential, because basically what happens is I can, if I remember how I used to think about the ECH differential, essentially the parts that were just covers of R cross gamma, I can just replace with, I can just add in trivial cylinders. So if I have some curve in this moduli space, I can think of sort of the curve in the usual way as this curve in this moduli space, along with some trivial cylinders over gamma. So the final thing to talk about in the definition of the ECH is the partitions of the ends of holomorphic curves that contribute to the differential and to basically everything that's important in ECH. So so what the partitions do is they say that if you have a curve that's important for ECH, then it tells you the actual ray of orbits that the ends of those curves land on. So so I said all that we care about is the total multiplicity of the ends of the ray of orbits, but the partition conditions actually tell you that under certain, so if your curve satisfies the partition conditions, which is this big proposition that I said you should read the index inequality paper to fully understand. If your curve satisfies these partition conditions, then the ends are on certain fixed orbits. So like if like I said, if there's an orbit gamma that appeared in alpha with multiplicity 2, based on the rotation number of gamma, we could know whether or not it's a double cover or 2 single covers. If it appears at the end of a curve in one of the moduli spaces that ECH is interested in. So so there are these 2 partitions that we're going to be interested in. There's P in and P out. So P in is I think in later literature it's called P minus. It's the thing that appears usually at the bottom ends of curves, and it's the set of horizontal displacements of the lowest convex lattice path above the line y equals theta x for x between 0 and m gamma. So m gamma is the multiplicity of the orbit, and theta is the rotation number of gamma. So let me just do like a super quick cartoon of an example. This is probably just going to be a very trivial example. So if this is my line, so let's say theta is a little bit less than 1. So then, and m gamma is 2, then I've got this line here. And if I want to consider the lowest path, then I'll be considering that path. So then here I would get P in of gamma of 2 is going to be 1, 1. And if I have the same situation for P out, so P out is defined similarly, but it's the horizontal displacements of the highest concave lattice path below the same line. So here it's going to be this. So P out in this situation is going to be just 2. And an important fact that's proved later in the paper that we're not going to prove is that these partitions depend only on theta mod z. So if I change my trivialization in which I compute my rotation number, then I'm going to get the same partition. So even though this rotation number only depends on the trivialization I pick, mod z, I actually am fine. These are well defined. Okay, so some facts about partitions. So there's a partial order on the partitions. So if I have 2 partitions and a irrational number, so if you remember, ECH is defined, the initial definition is for a non-degenerate contact form. So the rotation numbers of elliptic orbits are going to all have to be irrational. so if I have an irrational rotation number and two partitions of an integer, then I say that P is greater than or equal to, with respect to theta, P prime, if for all elliptic ray orbits gamma with rotation number theta, there's an index 0 branched cover of R cross gamma with positive ends at covers of gamma given by P and negative ends at covers of gamma given by P prime. So here I would say, I mean, I don't know if this curve exists. I would have to compute some things to show that it does, but say like P is, oh, actually. So P in is always maximal and P out is always minimal. This is a lemma proved in this gluing paper. And so, on my previous slide, I showed that P in was 1, 1 of 2 is 1, 1 and P out of 2 for this value of theta is 2. So this tells me that there is an index 0 branched cover of a trivial cylinder that looks like that. So by a pair of pants, as Yuan talked about last week. So this is a consequence. And the index is equal 0. This exists by the lemma. And the previous page examples. Okay, and then a final note is we always think of partitions as being written in descending order, so the largest number first, and then you can concatenate them. So we're going to be doing that several times later. So if you have two partitions in descending order, and then the largest number in the second one is smaller than the smallest number in the first, you can just stick them together and you'll get a partition of the sum of the two numbers that you partitioned. And sometimes that partition, like sometimes if you take P out and P out and you concatenate them, sometimes that's P out of the sum of the numbers. Okay, so to prove d squared equals 0, we need to prove that a moduli space is compact, and then we need to identify the ends using gluing. So the first thing is I'll explain the compactness, and this isn't really as much the focus of obstruction bundle gluing. So we'll talk about this, and then hopefully we'll do this somewhat quickly and be able to get to to the gluing part. But there are several important definitions that are introduced while we're trying to prove this lemma. Okay, so I'm in the setting that I would need to be in to think about d squared equals d squared. So I have a generic J, admissible orbit sets, and a sequence of index 2 curves in this moduli space that I use to compute the differential in ECH. And I want the space to be compact, so I want, after passing to a subsequence, this sequence to converge to either another curve in my moduli space, which is fine, it just means that it was, this sequence was limiting to some interior point in my moduli space, or to a broken curve. So, so it's broken into into 2 plus some number of levels. And each of these middle levels is a union of R invariant cylinders, or is a cover of a union of R invariant cylinders. And then these outer 2 is what's called an ECH gluing pair. So we're going to prove first that that we get sort of this setup, and then I'll define what an ECH gluing pair is, and we'll prove we actually get an ECH gluing pair. Before we do that, though, I need to explain, or I wasn't actually going to include this proposition, and then I realized that throughout this entire talk, I cite it many times. So I thought it would be important to include it. This is the proof of this actually in gluing 1 is, I think, fully contained in gluing 1, but it relies on this other proposition, proposition 714, whose proof it requires a lot from this paper, index inequality for embedded pseudo-holomorphic curves and symplectizations. So, so I'm not going to explain the proof of this proposition, but this is kind of the key to everything. So this proposition is what tells us that if I know something about the ECH index, then I know something about the partitions of the ends. So what this is saying is, first, the ECH index is always positive. If the ECH index is 0, then my curve is just a union of covers of cylinders. So it's not anything interesting. If the ECH index is 1, then it can split into two separate disjoint components. One is a union of covers of cylinders of index 0, like in the first, like in this B. And then the second part is a Fredholm index 1 embedded curve, and with these partition conditions on the ends. So what do these say? I mean, I'm going to explain this now, and you probably won't remember it, and then we'll have to revisit this point multiple times to prove things later. So U has some number of positive and negative ends at gamma, and some of those ends are at the ends of this U1, and some of those ends are not. And so the conclusion of this proposition says that the partition of the positive ends of U1 agrees with the first entries in the outgoing partition of the total number, or of the total number of ends at gamma. So I'm just drawing just the ends at gamma. So I have some, let's see, I had my outgoing partition of theta was just 2. So what this is saying is the positive ends are like my, so let's say M gamma here is just 2, M gamma plus is 2, and M gamma minus is also 2. Then the positive ends have to be the outgoing partition, and the negative ends have to be the incoming partition. So it has to look like this. And this is a curve. This isn't necessarily, this is in fact some index 1 cover. So maybe it isn't a genus 0 branched cover of a trivial cylinder. It could be just some index 1 curve. And the top has to be the outgoing partitions, the bottom has to be the ingoing partitions. And it's actually a little bit more complicated because in this example, I set M gamma plus to also be M gamma plus, or M gamma plus 1, and M gamma minus to be M gamma minus 1. So there are no, in this example, there are no covers of R cross gamma. But if there were covers of R cross gamma, then what this proposition says is that the ends in the index, in the Fredholm index 1 curve, have to equal the beginning of the outgoing or incoming partitions of the larger number. Oh, sorry, this is a typo. This should be in. I think I must have.
I was wondering.
Yeah, I think I must have wrote / in.
Yeah. Okay. Anyway, I was like, epsilon was P.
Yeah. I forgot to write text. Okay, and so then if I have an index 2 curve, then I have basically the same thing, but furthermore, an index 2 curve can only end on admissible orbit sets, and U consists of an index 2, Fredholm index 2 embedded curve, and then this covers of cylinders, and then the same sort of end conditions hold on the partitions at the ends of the index 1, or sorry, the index 2 embedded curve. So if you look in gluing 1, this proposition is written in a much more clean way, but that's because it relies on a definition that I didn't use for this talk. That basically is this. So, so the upshot is that if I know something about the ECH index, I know something about the ends. Okay, so sorry, so what we're doing, we're proving this compactness lemma. Okay, so proof. So we can pass to a subsequence using a Gromov compactness argument that's explained in this paper that I keep talking about. And the key idea is that there's an energy bound, so you can use a version of Gromov compactness. And if the limit curve is not broken, then we're done. And if the limit curve is broken, each component has index greater than or equal to 0. The sum of the indices is 2, using the additivity of the ECH index. And any index 0 level, or any index 1 or 2 level, has components with Fredholm index 1 or 2. So because the Fredholm index is also additive, that means that that means that the total Fredholm index is 2. So this means that if I have an index, actually, I think I explained this on the next page. No, I don't. Okay, so basically, what this means is that, either I have an I equals, so there's sort of 2 ways I can break. Either I have an I equals 2 level and all others are I equals 0. And then in this case, the I equals 2 level is also Fredholm index equal to 2. So all the I equals 0 levels are ind equals 0. So this is the first way to break. The second way to break is if I have 2 I equals 1 levels, but these are also ind equals 1. So we get that the I equals 0 levels are ind equals 0 again. So if I have a, basically the levels have the same Fredholm and the same ECH index. So now let's try and figure out what our broken curve looks like. So I'm going to just call these levels the names that I wanted to give them in the compactness lemma. So so this is the top level and this is the bottom level. So I have like u plus tau 1, tau k, u minus. This is towards negative infinity. So the next step is to show that the indices of u plus and u minus have to be 1. So this follows from, so if I can show that they're non-zero, then they have to both be 1, because if one of them is 2, the other one has to be 0. So that means that the index of the tau i's is also 0. And by this proposition, this great proposition that I keep talking about, they have to map, the tau i's have to map to a union of R invariant cylinders. So what remains for us to do now is to prove that the indices of the top and bottom levels can't be 0. So if they are 0, then again, by this proposition, they're a cover of cylinders. And the partitions of the ends have to equal the partitions of alpha from the limiting curves. And by, so this is this proposition that I said that came before proposition 715. Basically, the partitions at the top ends of u plus have to be the outgoing partitions. But the problem is there are no, what am I talking about? No index 0 branch covers with top partition P out. Oh yeah. So, but why would it have to be a branched cover of this? Okay, maybe, sorry.
I think it must be like some index trick when you look at covers of curves.
Yeah, but I guess I'm not seeing why these have to be. Oh, sorry. If the index, yeah, sorry. It is a cover of cylinders by index 0. I'd forgotten the other thing I had just said. So it's a cover of cylinders by index 0. So u plus has to be one of these. And the top partition is P out. But that doesn't exist by this lemma where I said that P out is minimal under this partial order. And the partial order is that you can have a index 0 branched cover from one to the other. So P out can never have index 0 branched covers from it to something different. So such a u plus cannot exist. Similarly, the ECH index of u minus is non-zero. So I have these two index 1 curves at the top and bottom, and then index 0 curves in the middle. Okay, so now the next step is to prove that u plus and u minus are an ECH gluing pair. So what is an ECH gluing pair? So this is, this seems maybe unmotivated, but the way that we prove that d squared is, well, maybe it seems motivated to you, but the way that we prove d squared equals 0 really relies on this fact. I mean, it relies on everything, but it heavily relies, the combinatorics of the problem heavily relies on this B2. So So needed for the combinatorics in d squared equals 0. Probably shows up in other places too. So an ECH gluing pair is a pair from, so if I have like alpha plus, beta, and then alpha minus, an ECH gluing pair is some curve, you know, here. That's probably not going to happen. We'll do that. Okay, so the indices of the two curves have to be 1. And for each embedded elliptic Rabe orbit in just in either alpha plus, beta, or alpha minus, all the covers of that orbit are unbranched. And if the top or the bottom contains covers of R cross gamma with total multiplicity n gamma plus or n gamma minus, then the individual multiplicities have to be the outgoing partition or the ingoing partition. So this tells me about, so I didn't really draw any, actually I did. Okay, so let's pretend that this is some, well, this is kind of terrible. So, so I don't know, maybe it looks like this. I have something that does this, okay. Okay, so this would be legitimate because it's got, so the covers of R cross some elliptic Rabe orbit are different, right? So here are my two covers, this one and this one. I'm covering, well, this is a cartoon, so maybe it doesn't mean anything, but by the cartoon, these covers, these trivial cylinders should be over different elliptic Rabe orbits. And then the partition conditions, I mean, here they're trivial, but the partition conditions tell me about the partitions on like on here and on here. So how these orbits are actually partitioned. So if they're, you know, a cover of R cross, if they're just R cross gamma, or if they're R cross gamma squared or R cross gamma cubed, etc. So this is a pretty strong restriction on how these pairs at the ends of a broken, sort of limiting the broken curves can look at the ends of this index 2 moduli space. So we need to prove 1 and 2 and 3. So we need to show, so we've already shown this. So we need to show that all covers are unbranched, the partition conditions, and then we need to show that both can't contain covers of R cross gamma. So first to show that they're, so, okay, so for the second part, this follows immediately from proposition 715C. So I'll just mention that. And then for the first part, this again basically follows from the, I think maybe I'll just summarize this. So this again follows from the partial order on the set of partitions. So you can go through using proposition 715, see what your partitions on your top and your bottom have to be, and then see what the partitions of the cylinders have to be. And then you'll find that you can't have, that these components that cover cylinders cannot be branched. And then the third part, this relies on, excuse me, and a bunch of combinatorics in section 7.4 and 7.5 of the paper. But essentially the idea of the third one is that if I have covers of the same cylinder in U plus and U minus, then I can glue my covers of cylinders together from my taus, and using some combinatorics, I can show that I have to have at least one component that's a cylinder. But the problem is this is over an elliptic orbit, and these were the limits of something that was in a moduli space that didn't allow any elliptic orbits. So this would mean that I had started out with a cylinder over an elliptic orbit, which was not allowed. Okay, great. So I've proved compactness. And now I want to prove that d squared is 0. So I'm going to do this by proving that the coefficient in front of alpha minus in the differential square root of alpha plus is 0. When alpha plus and minus are admissible, the index difference is 2, and I have a generic j. So we're starting with step 2. We'll do step 1 later. So step 2 is I just write out how to compute this this differential. So what secretly I'm actually summing again over z plus and z minus, but I'm omitting that because these equations are so long. So I'm summing over all the moduli spaces. Summing over all the elliptic orbit sets that I've removed from alpha plus and beta, and summing over all these moduli spaces that don't involve elliptic, or taking the sum of the number of elements in all these moduli spaces that have no elliptic covers of cylinders, covers of elliptic cylinders. Okay, so that's just writing out what the differential squared coefficient has to be. And then this page, I maybe won't expect you to read all the formulas, but what's happening is I'm taking the GCD of these two orbit sets and then rewriting this whole thing, pulling the GCD out in front. So what ends up happening is, so this whole section is the d squared coefficient. And if I can show that each of these subsums are equal to 0, then I'm good. So that's helpful. So why would I go through all this trouble? Because if I can assume that my elliptic orbit sets have no common factor, then I can assume I'm using ECH gluing pairs, and my life is a lot easier. So that's step 2. So step 1 is then showing this equation when the etas have no common factor. Okay, so step 1. Okay, so I just repeated myself from the previous slide. And then I'm going to consider this one manifold. So this one manifold might be the thing you would normally consider when you're trying to prove d squared is 0, this part. And it's the space of index 2 curves between alpha plus and alpha minus. And I'm getting rid of the curves that are close to breaking. So this is in the sense of, Yuan talked about this last week, but so Yuan explained sort of what some elements of this set are.
Oh, and I just wanted to briefly interject. So whenever Michael says, like, we truncate the moduli space, this is, I believe, what he means by the truncated moduli space, where you're throwing away the curves which are close to breaking.
Yeah, and you choose these curves in such a way that they're like, that limits in this set of curves close to breaking, like always limits, the limits are always to the two curves that you wanted to glue together. So by the compactness lemma, this moduli space is compact, and its boundary, oh, and I guess, okay, so the final thing to say is that this, we can sort of substitute this, we can take out the curves close to breaking because we're allowed to sort of make them as close as we want to breaking. At least that's my sense, is that if I can show that, if I can use this moduli space, I can make them as close as I want to breaking, so I can sort of scoop up everything in here using this moduli space if I need to. Okay, so it's compact by the compactness lemma. So its boundary, it's a compact one manifold. So one manifold by for index reasons, and by this proposition that says the Fredholm index is the ECH index, and the boundary. So the boundary is the sum of the boundary elements is 0. So the new goal is to show. So this is what we want to show. This is our goal, our old goal. And if we can show that this left-hand side here is equal to this, then we get, then we're done. So yeah, so we want to show that the two things in the boxes are equal. Okay. So so the curves, so let's see, there's a number of things going on. So the curves close to breaking, I think I alluded to this just a few minutes ago, can be broken up into like the curves that they're going to be breaking into, and then neighborhoods of those curves. So as I said, as in Yuan's talk. The compactness lemma, if you go through the compactness lemma, it basically gives us a way to write down what the boundary of this compactified moduli space is as the sum over all curves that are going to break into one of these buildings that we talked about in the compactness lemma. And then you sum over all homology classes, and then elliptic orbit sets dividing alpha beta and alpha plus beta and alpha minus, and then sum over all orbit sets beta. So here beta is not admissible necessarily. So yeah, so here's what I said. So U plus U minus is an ECH gluing pair breaking along beta. They're in the homology classes Z plus and Z minus, and gamma plus and minus are elliptic orbit sets with no common factor. So that's part of being an ECH gluing pair. So now we just need to show that this thing is the counts of boundary points of this thing is equal to this thing. So maybe a little bit easier because I'm seeing some commonalities here. In fact, what that means basically is I can just sort of get rid of all of this stuff and get rid of all of this stuff and just show that what I need to show is this equation. The sum over the gluing pairs of minus the count of the boundary points of VU plus U minus, so that the set of curves close to breaking is equal to this product of counts of moduli space, if beta is admissible. If beta is not admissible, then I need to show that, that this count is 0. And I rewrote this right-hand side like this. So this is where I started going a little bit off piece. I'm sort of combining stuff from gluing 1 and the ECH lecture notes for the rest of the talk. So hopefully I did it in a somewhat helpful way. So I'm not going to talk about the signs, and actually at the end of the talk, I'm just sort of going to give up and just say the differential is 0 mod 2. But I wanted to just remind you that there are signs and you can work them out and show that the differential is 0 with Z coefficients. So what we have to do is to understand the ways that we can glue the ends of the U plus and the U minuses so we have this U plus and it's got some index 1 curves. And then it's got some covers of cylinders. And then U minus has got, some index 1 curves. So this is U plus, this is U minus, and it's got some, maybe this is a double cover. It's got some cylinders. And let me make this a little smaller and move it up. Make this a little smaller, move it down. And so then we have to be able to put something in between them. And because this is a gluing pair, these curves here, or these orbits here and these orbits here on the trivial cylinders are not the same. So this is like some gamma plus, or no, gamma plus is bad. This is like gamma A and this is gamma B. I don't know. These are different orbit sets. And so all of the ends that are at ends of covers of trivial cylinders in U plus have to match up to ends. Maybe they match up in some funny way. They have to match up to ends in the index 1 part of U minus, and then the covers of trivial cylinders in U minus have to match up using some funny branch covers of trivial cylinders to the ends in the index 1 part of U plus. So this is the reason why using an ECH gluing pair and assuming that gamma plus and gamma minus don't have any common factors is so helpful. So what we need to do is basically we need to count the number of ways to do this kind of thing and relate it back to this number. Okay. And I realize now that there's this minus sign that I may not have taken account of, but if we're just gonna count mod 2, then it doesn't matter. Okay, so this is the big theorem of the gluing papers. So it says that the number of ends of the set of curves close to breaking into U plus U minus is given by the same product of signs times a product over all embedded Rabe orbits in the ends at the net where in this curve beta, or sorry, in this orbit set beta that U plus and U minus meet over. So this is a product over, so beta, so this is a, let's see. Yeah, it's a product over all gamma and beta. At least in this setting. In general, so in general, it's a product over all orbits where U plus is a negative end at cover of gamma. But for us, that's the same as the positive ends of U minus. Okay, so C gamma is basically the ways to glue the ends of U plus and U minus together, and it's got a combinatorial definition. If gamma is hyperbolic, it's not that complicated, but if gamma is elliptic, it's very complicated. Well, I mean, this has got a long definition that takes several pages, and so I'm not going to tell you what it is. And the gluing papers, I mean, this is the main theorem of the gluing papers. So this is a big theorem, so I can't explain it, but I'll just explain what we need to do to show d squared equals 0. So we need to show that if gamma is hyperbolic, then C gamma is 1, and so it doesn't affect the product at all. So, right, because we need to show that that this coefficient is the number of ways to glue. So we sort of know that C gamma should be the number of ways to glue, and we need to show that the number of ways to glue is just 1. For each, so maybe I'll put this actually here. So just remind yourself that this is the number of ways to glue. And again. Okay, so for each, and by glue, I mean insert these tau 1 through tau k in between U plus and U minus in the building. So for elliptic orbits, Hutchings and Taubes show that C gamma is equal to this thing, and I will explain what it is momentarily. It's equal to something that depends on the multiplicities of the covers of trivial cylinders in U plus and U minus. So I didn't tell you so I've told you what everything except the factorials mean. And then for the final piece, if beta is not admissible, then that means that some hyperbolic orbit has multiplicity greater than 1, and we need to show that in this case, the number of ways to glue is 0. Okay, so for the first part, if beta is admissible, I have one hyperbolic end at the top or at the end of U plus, so U plus is doing something. I don't know, maybe it's connecting some things together, and this is hyperbolic, and I have one hyperbolic end at the top of U minus, and there's only one way to cover them, with a branched cover of a trivial cylinder over that orbit. So there's just one, so C gamma is 1. And also C gamma is 1 by definition of C gamma. This is probably the easiest. If you, of all these ways of, if you go to the definition of C gamma in section 1 of this paper, this is probably the easiest computation to figure out what C gamma is. Okay, so now let's assume gamma is, so we've done this. Great. So now let's consider the second case. So I will explain to you what this factorial is. So if n appears Rn times in P, so say like P is like is n, 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 m, m or something, then Rn is equal to 3 and Rm is equal to 2, for example. I don't think, well, I'm not sure if that would ever be a P in or a P out. Then this is just some number that you can define. So it's the product over all n's of n to the Rn times Rn factorial. So here, for example, P factorial would be the product over 3 and 2. So this would be 3, this would be n cubed times 3 factorial times m squared times 2 factorial. So just some number. And it will become clear, like sort of, hopefully it'll become clear why, like what the use of this definition is in another slide. So because the pair u plus u minus is admissible, either n gamma plus or n gamma minus is 0. So remember that n gamma plus or n gamma minus, this is the number of covers of R cross gamma in u plus, sorry, not gamma plus minus, in u plus minus. So because it's a, sorry, not admissible, this is wrong. This should be an ECH gluing pair. Admissible was this other definition that I was trying not to make. So because it's an ECH gluing pair, if you go back to the definition of what an ECH gluing pair is, only one or the other can contain covers of R cross gamma for a given orbit gamma, given elliptic orbit gamma, not both. So either n gamma plus or n gamma minus is 0. So let's just assume n gamma minus is 0 because it's easier. If you go back through, this means that gamma to the n gamma plus has to be an element of gamma plus, the elliptic orbit sets that we're dividing out from the moduli space to consider u plus. But if you don't remember all that, don't worry about it. So then if you go back through, there's a convention that says that P, so if P is just the partition 0, I don't know, if P is a partition of 0, then P factorial is equal to 1, kind of like how 0 factorial is equal to 1. So in that case, P in factorial is going to be, of 0 is going to be 1. So we need to show that the number of ways to glue the elliptic ends is this, right? That's what we have to show. And so now we just have to show the number of ways to glue the elliptic ends is just P out gamma and gamma plus factorial. Okay, so maybe that doesn't seem simple, but it is, well, it's simpler. So if n gamma plus is also 0, there's exactly one way to glue, and this is a proposition deeper in gluing 1. And this is because by the conditions on u plus u minus being an ECH gluing pair, there are, not on it being an ECH gluing pair. This is from proposition 715 C. So index 1 curves are going to have negative ends given by P in and positive ends given by P out. And so because P in is maximal and P out is minimal, there is an index 0 branched cover to connect them. And this proposition says there's exactly 1, which is good because if n gamma plus is 0 also, then this is 1. Okay, so now let's assume it's non-zero. Because u plus u minus is an ECH gluing pair, the multiplicities of the covers of these cylinders, trivial cylinders over gamma in u plus, are P out gamma of n gamma plus. That's just part of the definition of ECH gluing pair. And then because, so again, here's this proposition 715C showing up again, the multiplicities of the ends of the index 1 part of U minus are the outgoing partition of the total multiplicity of the number of times gamma appears in beta, which is the orbit set U plus and U minus are breaking along. And again, so here's just a little bit of discussion about this, but basically U plus U minus is an ECH gluing pair. So U minus can't have any covers of R cross gamma. So all the gammas have to appear in the index 1 part of U minus. This is the index of U minus. Okay, and then an earlier proposition about index 1 curves says that the first part of P out M gamma is equal to P out gamma and gamma plus in this situation. I think that's true. Yeah, so this is where the combinatorics of the incoming and outgoing partitions are a little bit confusing to me. But so in any case, what's happening is, okay, so what's happening here, I'll scroll down, see if I didn't really give myself enough space to draw anything. So what's happening is, maybe I can add yes, we'll add a page. Okay, so what's happening is I have this something here that's like this is my index equal to 1 part of U plus. And then I have some covers of, say these are all covers of R cross gamma for the same gamma. And then maybe this end is also on gamma, and this end is like on gamma prime or something. So this is gamma, sorry, not gamma prime, gamma, gamma, gamma. So then because U minus is an U plus U minus is ECH gluing pair, all of these have to be in, so maybe I have, I don't know, maybe I have some non-trivial cylinders or something. But all of these have to be in the, this is like the ind equals 1 part of U minus, and then the only trivial cylinders could be on a different part. And so based on the partition conditions and the fact that the index is 1, there's some subset of these that have the same partition as, so there's like the partitions always match. And then there's some other partition here, which is always P in, and this is always P out. So by this by the fact that there's always an index 0 branched cover from P in to P out, there's always something that goes here. This is prop 726. There's always exactly 1. And then the other thing that we have to do is we have to consider all the ways to match the same partition to the same partition. So these are both P out gamma of n gamma plus. So this is P in, yeah. So I have to consider all the different ways to match these things up, you know, so I could do something like that, or I could maybe have something that like does, I don't know, something that does that, you know, there could be a bunch of different ways that I could connect all of these things with index 0 branch covers of cylinders. But P, basically the partition factorial is exactly what counts all the different ways to match the ends. So the thing I was saying, I was talking about how the thing I'm confused about is I can put together, you know, that there is some subset of the ind equals 1 part of U minus that has the same partition as P out. But I'm a little bit fuzzy on why I can't sort of mix these regions. But I will just, I think it has something to do with the ordering that you pick on the orbits, and that's something I haven't talked about at all. But if you're actually going to consider the actual moduli spaces between these curves, you have to put an ordering on the Rabe orbits. And so that, I think, forces you to match certain curves to certain curves. Could be wrong. But so, oh, I had a lot more space. Anyway, okay, so maybe to convince you, so I'm not going to be able to prove that P out factorial is the number of ways to match the ends, because that's pretty hard in general. But that's what the last two sections of, or the combinatorics of that is two full subsections of the gluing one paper. But I'll show you, I'll sort of try and convince you in the simplest settings. So if the partition is just 1, 1, 1, 1, 1, then I have, you know, say I have like 4, or maybe I'll just do 3 orbits on the top and 3 orbits on the bottom. And then the ways to match them are just the different permutations, because I can match, so I can match, like, I need a lot more space than this actually. Draw a line. So I can match, you know, I can match in a straight line, but I can also match, and okay, so you might argue these are all the same orbit, but they do have an ordering, or they do have sort of different identities because they come from different parts of U, at least the bottoms come from different parts of U minus. And when I actually do this all precisely, I should also be fixing an ordering on the curves at the top. So I can do this. I can do this. You know, so basically, so maybe you can believe now that that the number of different ways to connect cylinders between these things, trivial cylinders, between these ordered sets of 3 distinct single covers of this orbit gamma, there are 3 factorial ways to do it. The other way is if my partition is just one single n gamma plus fold cover of the orbit, then I should get n gamma plus different ways to connect. And so maybe I'll just, I don't really know how to draw this. So, but I have a double cover and another double cover. And basically I can do the identity, or I can do the one where I go around one click. So I send this to this. And I send this side to this side. Well, anyway, I'll be sort of twisting halfway around the orbit. And you can imagine that if there are, this is an n gamma plus fold cover, then I have n gamma plus ways to sort of twist. And then if I have some more complicated partition, then the partition factorial tells me different ways I can match things up. Okay, and then the final thing is dealing with the non-admissible betas. So if I have a positive hyperbolic orbit that appears with multiplicity greater than 1, then the ECH partition condition, so this is basically taken from the ECH lecture notes, which this is an argument from the ECH lecture notes, which use Z mod 2 coefficients. So the argument in the gluing paper, because the gluing paper sort of explains a lot more about the C gammas, basically just says, like, compute the C gammas in this situation and you'll get 0. But since I didn't explain to you what the C gammas really were, I'll explain the argument from the lecture notes instead. So the ECH partition conditions, there's a partition conditions for hyperbolic orbits as well. I only told you the partition conditions for elliptic orbits, but there are ones for hyperbolic orbits too. And so you can show that they hold for gluing pairs if J is generic. Tell us that M gamma has to be partitioned in this way that's just 1, 1, 1, 1, 1. So there's MN. So just as in this example here, there are M factorial ways to glue, and that's an even number if M gamma is greater than 1. So And then if you want to figure out the sign, you have to work a little harder, or you should maybe read section 4 of gluing 1. And then if I have a negative hyperbolic orbit, then the partition conditions are given by these. And then if I basically using the same thought processes as the previous example, so I have this factorial from swapping the 2's, and then I have this 2 to the m over 2 floor from doing my twists. So this is the twists, and here's my swaps. Then I get, again, an even number of gluings. And I just have a page of nothing. Great, so now you maybe, if you need to understand the details of why d squared is 0, you have a roadmap to reading gluing 1.
Thanks so much, Morgan. That was wonderful. So we should all definitely thank Morgan. Give you all the, or I guess, give you emojis. I've learned from students and postdocs, they really enjoy the emojis.
I do enjoy an emoji.
Sadly, there's no like holomorphic curve cartoons that included in Zoom's latest update.
I'll go up to my cartoon. So are there any questions anyone wants to be recorded asking Morgan? Yeah, she'll end.